Let's add now the complication of vertical structure. So we'll look at a stratified model, atmospheric model, so that we will have a vertical structure function, a horizontal or meridional structure function, and we will see how they are coupled, okay, in this linearized set of equations we'll derive. For when you have two structure functions, you will use the method of separation of variables, which quickly looking at something as an example is here a diffusion equation, a Laplacian equal to 0, and you can set this chi variable to be of two structure functions yy and zz, and then this equation becomes zz d squared y dy squared plus yy d squared z dz squared, and it has to be equal to b because their sum is in this case 0, so that's the separation constant. And if the sum is constant, then you can choose a random constant where each one has to be equal to that constant, in which case you can write this partial differential equation into two ordinary differential equations, which are then easy enough to solve because this is now a constant here. B is a constant, right? So you get these simple wave equations out of that, which we can take into our basic equations. What we are doing here is to linearize the system we want around a motionless hydrostatic basic state. So then this is the hydrostatic equation, this is the ideal gas law, this is the equation of state, where basically the density profile is closely related to the temperature profile with the scale height. Okay, that's all. And since we are assuming a motionless basic state, the basic variables have to be a function of z as well. So you now write your perturbation momentum equations in the x and y directions, dp dx dp dy, of course, and the Coriolis terms with the inertial terms. Here is our perturbation hydrostatic relation. This is our continuity equation, and this is our energy equation, where this is the forcing term, right? If you have heating, q dot, which we saw before when we were doing baroclinic processes in the tropical systems, we saw how q dot can give us the stretching and advection of vorticity and create baroclinic processes and explain the atmospheric dynamics in the tropics. Gamma here is Cp over Cv. So we can seek normal modes in longitude and time by assuming that u, v, w, rho, and p are solutions of this functional form we'll take. So u, v, w, rho, p remains meridional and vertical to be consistent with the background state, motionless hydrostatic background state with exponential I kx minus omega t. So as we did before, except we have added some complication here of the vertical structure. Okay, so write this the momentum and write the equations now with this transformation. So you have I omega u cap minus beta v v cap I k p cap and so on, and this is the equation of state, looking quite intimidating. That's our continuity equation. That's our energy equation with the forcing term now put on the right side. So we'll first transform the forcing function. Following the transformation, u hat, v hat, w hat, rho hat, p hat as a function of background density profile. Remember, when we say rest, the background state is in hydrostatic balance at rest, obviously the rho bar, the mean density, is much greater than rho plus rho prime. So whenever you have 1 over rho, it'll become 1 over rho bar, which is the case here. right? I should have made that clear. Now we are using that here in defining these transformations, and we are defining the vertical structure function which we will use to write the energy equation. Here is our forcing term still. So did I jump something there? No. Okay, we are fine, right? Okay. These are just equations, rather tedious, but we have to run through them. So this is now the energy equation. Z is the vertical operator now given by this very complex looking expression where epsilon is minus dHs dZ. So you have stratification, so you don't have just the top of the atmosphere or the top of the ocean sloping in the meridional direction, but you have each layer in the atmosphere. We are dealing with the stratified atmosphere having a slope in the z direction, okay, locally. So there is kappa, which is the standard R over Cp, okay. Obviously you cannot remember this by heart, so you have to just look at it and get comfortable with all the terms, okay. The scale height of the background state still remains. Kappa is this one. We are doing z direction as well here because of the vertical structure, and we are going to now transform the equation in terms of the meridional velocity as a function of latitude and height, because we have stratification, which can be written as sum of these structure functions in the meridional and vertical. Okay, this is we can follow Dickinson's classic 1967 paper where the forcing function, this one, which is quite fiendish looking, for a given vertical structure S and Z also can be separated in a similar manner to the variables. So it can be written as meridional structure and vertical the heating term in a meridional sense as well. So you can now write the forcing as beta squared y squared minus omega squared intrinsic frequency times S and Z times psi n y. So again, the forcing term also has a vertical and meridional function. Okay, so this should be Sn y. Okay, so this itself is split into its own meridional structure and vertical structure. Okay, so for a given pair of wave number and frequency, the meridional structure is an eigenfunction of this equation, which is transforming, as you can see, this expression and giving us this equation, which here Hn is the separation coefficient or equivalent depth of a family of shallow water equations. Okay, here is the separation coefficient. So since the atmosphere is stratified, we are going to assume that each layer is like a shallow water system. So you can then just write the equation in this complex form with this forcing function, scale height, and the vertical structure with these coefficients A1z and A2z, where these are again very complicated looking long expressions. Okay, so we are basically, just like we did before, replacing H and U with just Vy. We're going to replace U and the forcing with the vertical structure and meridional structure functions, and then look for their coupling. So the horizontal structure equation that emerges out of this equation is this one, d squared psi n y squared plus this expression here, which is full of dispersion relations of the waves, times psi n equal to 0, and the equation is somewhat similar to what we saw before when we had just horizontal motion and no vertical structure. So in that case it was d squared v dy squared, and a similar looking thing here, some differences rearranged, but v equal to 0. Here c squared is now, in our case of vertical and horizontal structures, the gravity speed is GHN, where HN is a layer, not the equivalent depth, right? So c squared before was GH bar in the uniform case with no vertical structure. Okay, so let me close this here and come to the solutions of the equation that we are seeking by linearizing and then separating into vertical and meridional structures, and see how the two are coupled. That's a more realistic situation, even though we are still dealing with very simplified background state of hydrostatic balance stationary flow.